Firas Saggaf, and I'm gonna talk about the applications in our presentation. In application, we can use our robot to the agriculture, warehouse, industrial, retails, and it can be modified as monitoring robots, delivery robots, pickup and drop of robots, and harvesting robots in many ways. In this part, I'm gonna talk about the algorithms that we use in our robot. We have something we call SLAM. What is SLAM? SLAM is simultaneous localization and mapping. How the robot build a map and figure out its position in the map. Here we use the SLAM. SLAM has three different algorithms. Each algorithm has its advantages and disadvantages. And first of all, in the algorithms that we have here is G mapping. In G mapping, we have something we call RPPF. RPPF, Raw Blackwell's particle filter. It's a method, guess and check method, where the robot creates many possible position we call particle, then keeps the best matches to the laser scan and discard the rest of them. In G mapping also we use 2D LiDAR, we cannot use 3D LiDAR. Also in G mapping it depends on something we call odometry. What's the odometry? It's used by the robot to estimate its movement and its position over time by measuring the motion of their wheel. Also the robot's encoder wheel count how much each wheel has rotated, and from these rotations calculates distance traveled and calculates change in angle. Also in G mapping we cannot use it for huge map. We only use it for small area or indoor map. The second thing we have here is the cartographer. Cartographer uses graph-based optimization with some maps. It builds small local maps, we call it submaps, then connected into a graph like puzzles pieces. You want to see the entire picture, you need to puzzle it to pieces. So in cartographer also after that adjust the graph if there is error or no. In cartographer we use odometry. Also if we don't want to use the odometry, it relies on scan matching. In cartographer the limitation is using high computing power, and it's only using 3D LiDAR for massive area. We cannot use for small area or short mission. The third thing we have, and the last one, is HectorMap. In HectorMap relies on something we call scan matching. Scan matching compares new scan laser scan to the past one. Also in after the comparison calculates the best alignment, like overlaying two pictures. In HectorMap we don't need odometry, it's purely LiDAR based. Also it's only 2D LiDAR, and the best thing is fast lightning. Also it's just for small area or short mission. Okay, in this slide I'm going to talk about the G mapping. We choose G mapping in our robot because we set up the 2D LiDAR in our robot, and we don't want to use our robot in massive map or massive arena or huge arena. So in Gmapping also, what is Gmapping? It's an open source. It has many libraries you can use, and you can adjust them and you can share them as you want. So also the Gmapping is enables you to build a map and determine your position in that map. So that we all need in our robot. What we use with Gmapping, we use 2D LiDAR and odometry data from the encoder's wheel. So what's the back ends of the Gmapping? The back end of the Gmapping is the 2D occupancy grid, which shows you many cells and which cells are marked as occupied, which cells are marked as unoccupied. So how Gmapping work? What's the principle of working of Gmapping? In Gmapping work, we have here as collector sensor data. First step we have is collector sensor data is collecting the data. The robot collects the data from the LiDAR to see obstacles and collect the data from the odometry to know its movement or its position. So ROS here, which is a robot operating system, automatically handles this by publishing the data on a special topic. So here in the next step we have is the prediction. In the prediction, the robot predicts the next step or the next position of it. And the prediction, each particle, which means guess of robot's position. The guess, what do you mean by guess? Guess is an the robot estimate the robot's current position and orientation in the environment. So each particle is moved according to the odometry readings in prediction. And also we have something we call motion model. Motion model where the robot might be in the next movement, predicts where the robot might be in the next movement or next position. So the robot predicts it moved by using its wheel data. Here in the prediction step, here we have the correction step. In the correction step, we compare the predicted map and the real world map. How we compare them? We have something we call weights. The weights, we calculating the weights. So what's the weights? The weights in the back end of the Gmapping, we have something we call occupancy grid. In the occupancy grid has many cells. In each cells has weights. It might be high weights, it might be low weights. So the differences between predicted scan and the real scan is measured. So if they match well, it's high weight. If they don't match, it's low weight. And this is bad guess in the low way. So the robot checks how good that guess is by comparing its predicted LiDAR scan and with the real scan. This is in the correction step. Step 4, we have resampling. In resampling, the robot select the weights, the particles of higher weights that are filtered by the correction step. So the particles with higher weights are duplicated in the robots, so to keep more of the good guesses, and the low weights, the particles with lower weights are removed, so the robots doesn't want more bad guesses. So why we have resampling in the G mapping to focus more computational on the best guesses. So to stop wasting time with bad possibilities and bad guesses, and that this step makes the algorithm go faster and more accurate over time. So in step number 5 is update the map. We use LiDAR to update the map. The LiDAR scan is taken at the robot's position at the robot's current position tell us where the obstacles. So the map is an occupancy grid, which is there are many cells. Each is marked as occupied, which mean obstacles or walls, or some cells are non-occupied or unoccupied, which mean it's free space to walk, and others are unknown, which not yet observed. So in this last step, update the map using the latest sensor data from the LiDAR.